Hello everyone. In today's video lecture, I'll be explaining how to separate respiratory signal from PPG signal using FFT and IFFT, and then to find out the respiratory rate. So let's get started. So first of all, what exactly is FFT? FFT stands for fast Fourier transform, and it is an algorithm to compute DFT, discrete Fourier transform, and its inverse. I already explained what DFT was in the previous lecture. So we know Fourier analysis converts the signal from original domain, that is a time domain, to frequency domain and vice versa. So DFT is obtained by decomposing the sequence of values into components of different frequencies. Now what FFT does is it rapidly computes such transformation by factorizing the DFT matrix into a product of sparse factors. This is because the DFT in calculating a DFT by the matrix method may take up a lot of time, and we want to reduce this complexity, the time complexity. So that's why I use FFT. So as a result of using FFT, the complexity of computing DFT reduces from big O of n square to big O of n log n, where n is the data size. This is the equation part of the DFT. This is what a DFT looks like. So here we are dividing into two parts. One will be the odd part, even part, and this will be the odd part. That means this will contain the even samples and this contains the odd samples. And this goes on. Finally, this can be written in this form. So basically it is nothing but the concept of recursion. So let's see how we'll be implementing this on an Arduino Duo board. Here we will be using a library that is called Arduino FFT.h for our calculation. It has inbuilt functions that we're going to use for calculating the FFT and IFFT. Now here the message size is 750, but you can see we've taken the sample size as 1024. This is basically because while doing the recursion, at each step we'll be dividing the signal into two parts. So that means we need a signal size which is somewhat to the power of 2. Like the signal value size should be power of 2. So since we are having 750 values over here, and the nearest value 2 multiple of 2 is 1024, not multiple of 2, power of 2 is 1024. So we'll zero pad this signal. 750, after 750th value, we'll be zero padding this till we get the size to be 1024. And here are the rest of the variables. Here we're initializing the real and the imaginary part to 0 initially. Here we're applying the moving average filter, which I've already told in my previous videos. And here we are calculating the mean as well. And finally we are subtracting the mean to get proper signal without any disturbance or distortions. Now this here is where the FFT calculation actually works. This function FFT.compute period, the imaginary samples and FFT forward gives us the forward FFT part. So here sample size is 1024, and here we are calculating the magnitude response of this FFT signal. So you can see this is the square root of imaginary part, square of imaginary part plus real part. Moving on. Now, how we want to separate this respiratory signal from the PPG signal? So the procedure that we will be following is this. We know that our respiratory rate frequency is from 0.05 Hz to 0.5 Hz, and beyond that it will be PPG signal. So what we will be doing here is, we know that F is equals to K into capital Fs divided by N, which I already told in the previous video. So we know here F is 0.5 Hz, that is the maximum value to which respiratory rate can be there, and Fs is known to us, and capital N is 1024 over here. So using this we'll find an index, the sample index over here. So we will consider, so like suppose we got sample index as 21 over here. So we'll be considering the first 21 values and the last 21 values in the FFT signal, and the rest part of the signal will make it to 0. So this will give us the FFT part of the respiratory signal only. Using this, we'll perform IFFT to get the original respiratory signal. Similarly, to get the PPG signal, we'll put these two parts as 0 and the middle part as the value, and then perform IFFT on it to get our PPG signal. So basically this is the implementation of that. Here we are finding the maximum index value, as I already told you before that in the previous experiment as well. To find the period or the frequency, we like in this 21 samples, we'll find the maximum frequency component, like the one with the highest frequency, and that will again apply the formula I told, f is equals to k into fs by n, to get the frequency, and that frequency shall give us the rate or the beats per minute. So this is the equation. This is actually nothing but the implementation of that. Here we're finding the maximum index for this using this function and all. So this is basically what I've explained right now. Here, now here we are computing the reverse FFT. So one is for the respiratory signal only, and one is for the PPG signal. And then we are converting it to the magnitude, getting the magnitude response. And finally, we are printing all of these. So let's see what are the results that we obtain. This is the FFT of the complete signal. So you can see we are having peaks at the ends, and in the middle part there is this flatter portion. Now, after removal of signal from PPG and respiratory part, this is what we obtain. So the blue one is the signal, like after removing the PPG part, the only respiratory part, and red one is the signal with only the PPG part and not respiratory part. Now this is what we have extracted. This one is the PPG signal. You can see it is almost in the form of the PPG signal, and the one below is the respiratory signal. So we obtain the index of the maxima in the PPG FFT plot, that is the respiratory part, as 12. So equating it, multiplying it with Fs and dividing with 1024, we get the frequency value 0.293. Again multiplying with 60 will give us the beats per minute, that is 17.58, which is pretty much correct to the original value. Now we're again implementing the same thing on MATLAB. So we'll take the value, we'll perform the like PPG part and respiratory part, will make the arrays, and we'll zero pad it over here. And here we directly have functions inbuilt in it, FFT and IFFT, to get the values. So we don't have to do a lot of things. Basically, we're just plotting all the values so that we can observe the exact output. It becomes quite easy in MATLAB as compared to Arduino. Let's see what results you obtain. So these are the plots that we actually obtain. This is the actual PPG with the respiratory signal only, and this is the FFT. This is similar to the one we obtained. Now we remove the PPG signal, so you can see only these parts are left at the beginning and at the end. And also we remove the respiratory part, so you can see this part is what we get. And this is the extract PPG from this signal, and this is the extract respiratory from this signal after doing IFFT. And you can see this is pretty much similar to the plots that we obtained in the previous one. Here the index that you obtained for plot is 10, and the rate is 42.65 beats per minute. Pretty much same what we obtained there. With this, we come to an end in this video tutorial. So I hope you understood what I want